We have stoichiometry, which is balancing chemical equations and converting. Balance a chemical equation. To balance a chemical equation, remember, we want, typically, there's only one real exception to this. Typically, we want the lowest whole number values for all things where every atom is equal on both sides. Every atom is equal on both sides. Now, in this case, you want to look at the elements, how they appear. This one has a carbon and a hydrogen in one compound, a carbon on one compound, hydrogen on one compound, and oxygen here, but in two places there. So the easiest way to balance this is carbon and hydrogen first and oxygen last. But we have to kind of play around with things. So one carbon, so I'm going to go and leave this as 1. I may change this later, but leave that as 1. 4 hydrogens, 2 hydrogens, so I have to double up. So now we have 2 hydrogens times 2, or 4. 4 and 4. 2 oxygens, 2 oxygens, so we have 4 oxygens here. That means I would need 4 oxygens there, so I double that there. That would be our balanced chemical equation. Sometimes you might have a nasty thing, like we'll say C2H6. This one might be this one's going to be a little bit harder. Because you're going to go, okay, 2 carbons, 2 carbons. 6 hydrogens, we need 6 hydrogens. But here's the problem. 2 times 2 is 4. 4 plus 3 is 7. 7 divided by 2 is 7 over 2. That's a fraction. We don't want a fraction if we can help it. So how do we get rid of a fraction? We're going to multiply everything by 2. So we double that. That becomes 2. Double this, 7 halves. That becomes 7. Double this becomes 4. Double this becomes 6. The only time a fraction is really allowed is when you're doing the enthalpy of formation. Like if I'm calculating the enthalpy of formation of CO from its base elements, carbon and oxygen, because I'm specifically calculating the formation of 1 mole CO, we're allowed to use a half. But any other time, we typically want a whole number. Because it's prettier for one. So one more balancing before I move on. Like Fe2O3 and Mg. Let's see. Goes to MgO and Fe. This in mind, we have to balance right now the magnesiums are balanced, but the oxygens aren't and the irons aren't. Sometimes you have to go systematically one at a time. We can start with the iron. 2 irons. Now the irons are balanced, the magnesiums are balanced, but the oxygens aren't. So what we're going to do is, you're going to balance the oxygens. 3 oxygens, 3 oxygens. But now the magnesiums are out of balance. 3 magnesiums, 3 magnesiums. And now they are balanced too. So with that in mind, That's how we balance these guys. Now, why do we need to balance these guys? It's so we can go, previously we went from atoms to grams, but we also have to go from grams of compound A to grams of compound B. Now, because each compound has a different weight, each compound can't be directly compared. So what we have to do is go to moles. We're going from grams of A, so we're going to grams of A to moles of A. And then we're going to use the balanced chemical equation to find the moles of B. And then we're going to turn it back into grams of B. This is the basics here. The basics. So if I'm using, I'll use the iron oxide magnesium situation. If I had 225 grams of iron oxide, how much magnesium do we need? Mg. This is easy. Once we understand this basic premise and have our molar masses. Good. So we start with our 225 grams of iron oxide. Once again, we're going to cancel units. Remember, we already determined the molar mass of this to be 160 grams of iron oxide for 1 mole of iron oxide. Now we will use the balanced chemical equation to figure out how many moles of magnesium will be needed. Well, there's 1 here, there's 3 there. So for every 1 mole of iron oxide that we have, it will require 3 moles of magnesium. And then finally, we need the molar mass of magnesium. 1 mole of magnesium, if I'm not mistaken, is 24 grams. So this is converting grams of iron oxide to grams of magnesium. I could just as easily convert it to grams of magnesium oxide or grams of iron, but I am converting to grams of magnesium. We're allowed to convert to any other mass unit in one single balanced chemical equation. So 225 divided by 160 times 3 times 24. You do that, you would get 101.25 grams. So starting from, 101 grams of magnesium. That is the basics of stoichiometry. Now there's 2 other ways we're going to use stoichiometry. So I'm going to continue with this. So that we're going to use this when we have to deal with limiting reagents. And we're going to have to deal with this stoichiometry when we deal with percent yield. So let's write a new chemical equation. We'll say, let's see. Let's see. We'll go back to our balanced chemical reaction of this guy. We had CH4 plus oxygen. 2 oxygen goes to CO2 and 2H2O. We'll go with that. A limiting reagent problem. Limiting reagent is when we have masses of both reactants, or masses of at least two out of the reactants, and we're asked how much of a product could be formed. How much of a product could be formed? And the idea is that one of these guys will run out first. Whichever guy runs out first will limit how much a product could be formed. If I said I had 18 grams of methane and we'll say 51 grams of oxygen, and I asked how much CO2, much CO2 would be produced when we burn this. To do this, the easiest way to do this is literally to go grams of methane to grams of CO2, then grams of oxygen to grams of CO2, and then check the lowest number. The lowest number will be the correct number because it comes from the limiting reagent. So 18 grams of methane. Systematically, carbon is 12, hydrogen is 1. It is 16 grams per one mole. For every 1 mole of methane, we use 1 mole of CO2. And CO2, oxygen weighs 16, so 2 of them is 32, so another carbon is 44 grams CO2. Setting up for oxygen. 51 grams of oxygen, 32 grams per 1 mole. And there are 2 moles of oxygen for every 1 mole of CO2. Mole CO2, 44 grams CO2. So I have my 2 problems set up. I must solve them. 18 divided by 16 times 1 over 1 times 44. If I burned all 18 grams of methane, that would produce 49.5 grams of CO2. If I burned all 51 grams of oxygen, so 51 divided by 32, divided by 2 times 44, I would only get 35 grams of O2. So really it's 35 and 50. 2 sig figs, 2 sig figs. So 35 grams of CO2 would be my answer. 35 grams of CO2 would be my answer because I choose the lower of the 2 numbers because it comes from the limiting reagent. The other aspect we will study with this is the percent yield. Percent yield is simply the actual yield, the physical measured, divided by the theoretical. So times 100. So another way to put that is the measured over calculated. All this that we've just done is a calculated yield. So in a theoretical yield, in a percent yield problem, you'd be asked something like this. If I had 51 grams of oxygen in the following equation, and I produced let's say 31 grams of CO2. 51 grams of oxygen, and I produce 31 grams of CO2. What would our percent yield be? Now, we would do all the same steps. We would take our 51 grams of O2, 1 mole of O2, 32 grams, 1 mole of CO2 for 2 moles of O2, and our 44 grams per 1 mole of CO2. All that would be the same. So we'd get 35. But then you would take one more step in that you would take 31, which are the measured or reported or whatever yield, divided by our 35, and would multiply that by 100 to turn this into a percent. So you still have to do the grams to moles to moles to grams, but you have to do one additional step after the fact. So the yield would be close to 89%, 88.6, but we're going to round to 89%. So that is the basics of stoichiometry. That is going to be a big thing that we're going to use and keep using all throughout Chemistry 1 and Chemistry 2.